Hello learners, welcome to NIOS Studio. Today we are going to talk about our topic semiconductor devices. In semiconductor devices, we will actually discuss about what are rectifiers. Let's start with our topic. In this particular topic, you will be able to understand what is the process of rectification. You will be able to explain the working of a half-wave rectifier. Similarly, you will be able to explain the working of a full-wave rectifier, and you will be able to list various applications of the rectifier. Till now, you have understood about the diodes and the transistors and their working. Now, let's have a look at some of the practical devices. So, now we will talk about rectifiers, which are also a kind of voltage regulators or power suppliers. Let's understand what do we mean by rectification. Now, as we are aware of a PN junction diode, in a PN junction diode, there is asymmetric electric conduction. By asymmetric electric conduction, we mean that whenever the diode is in a forward bias, there is a large conduction of current, which means that the diode offers very less resistance. In the reverse bias, the diode practically does not conduct, or else the diode ideally offers infinite resistance and blocks the current. This particular property of a PN junction diode is utilized in the process of rectification. Rectification means that we want to convert an AC signal to the DC signal. AC signal, if you are aware that in our households we are receiving AC electric current, which is at a frequency of 50 Hertz. By this, we mean to say that within a second, 50 times we are going to have a positive cycle and 50 times we are going to have a negative cycle. Some of our devices like the cell phone or the laptop do not use AC signal. They require a DC signal, and therefore we need to convert an AC signal received at our households into a DC signal. Thus, the adapters which you commonly use are kinds of rectifiers which convert AC signals into the DC signals. Let's understand the working of a simple rectifier. A PN junction diode is the simplest possible rectifier. That means a simple junction diode is capable of converting AC signal into a DC signal. A single PN junction diode can act like a half-wave rectifier, or else we can use a combination of two PN junction diodes and use it as a full-wave rectifier. Thus, to begin with, we say that there are two kinds of rectifications which are possible with the PN junction diode: half-wave rectification and full-wave rectification. Let's understand the working of each one of them one by one. This is the circuit diagram of a half-wave rectifier. In this half-wave rectifier, we have connected a diode over here with the help of a step-down transformer to the AC mains. The AC input which we receive is given here directly from the main supply. The step-down transformer steps down the voltage of the AC signal which we commonly receive at 220 volts. Now, the AC cycle, when there is a positive cycle, the diode is forward biased and thus it conducts and you get an output across the load resistance. During the negative half of the cycle, the diode is reversed biased and therefore the diode does not conduct. As the diode does not conduct, there is no output measured across the load resistor. So let's have a look at the input and the output of the half wave rectifier. For the half wave rectifier, figure A is indicating the input signal. So what we realize is that there is a continuous change. So you see a negative and a positive cycle simultaneously and slowly fed as the input to the rectifier. Now what is happening is, during the positive half of the cycle, we observe that the load resistance allows the current, and thus you observe an output in the positive half cycle. As soon as the negative cycle is fed into the diode is now in the reverse bias, and thus it blocks the current and does not allow the negative cycle to pass through the diode. So what we get is, all positive cycles are conducted through the half wave rectifier while the negative cycles are blocked. So thus the output of the half wave rectifier looks like what we see in figure B. In the half wave rectifier, during the positive half of the cycle, the diode is forward biased. In this case, the diode conducts and a large amount of current flows across the load resistor. During the negative half of the cycle, the diode is reverse biased and it blocks DC. The maximum amount of voltage which a diode leads to in the reverse bias is denoted by Vm, and it is the peak inverse voltage which a diode can bear. The peak AC voltage Vm is the maximum voltage across the diode during the non-conducting cycle. Corresponding to Vm, the DC voltage which is given out is Vm divided by pi. Thus, the current corresponding to this is Vm divided by pi into RL, because the current is VDC divided by the load resistance. Now looking at this, it is not a very efficient rectifier. It has a very low efficiency because half of the energy is blocked or does not pass through the diode. Thus, a half wave rectifier is rarely used because it is not an efficient device. To improve upon a half rectifier, the next we do is to have a full wave rectifier. Let's understand the working of a full wave rectifier. This is a full wave rectifier. In this full wave rectifier, we have two diodes D1 and D2 connected in the circuit to the AC mains. Over here, the voltage input in the form of an AC is fed into the circuit, and the step down transformer steps the voltage down to the specified value. Now, during one half of the cycle, the diode D1 is forward biased while the diode D2 is reverse biased. Therefore, the current conducts through the D1 and a voltage drop is measured across RL. For the negative cycle, D1 becomes reverse bias and does not conduct, but D2 becomes forward bias, and therefore D2 starts conducting, and the same amount of current is now across the loop and a voltage drop is measured across RL. Thus, for both the parts, that is negative part as well as the positive part of the AC cycle, one or the other diode conducts, making both the current flow through the circuit. Let's have a look at the output of a full wave rectifier. For a full wave rectifier, this is the input signal. So when we look at the input signal, we realize that we have a continuous positive cycle followed by a negative cycle and so on. during the positive cycle, the first diode, that is D1, conducts, and thus across the load we measure the voltage drop from D1. During the negative half of the cycle, the diode D1 blocks the current, but D2 starts conducting. Again, there is a voltage drop across the load resistor RL. Now, similarly, the process continues, and thus the final output is in the form of, for each positive cycle there is an output, and for each negative cycle again there is an output. So, what we realize is that the efficiency of the full wave rectifier is double the efficiency of the half wave rectifier, because over here the energy is not wasted each time you are going to get the output across the load resistance. Now, over here both the diodes D1 and D2 only conduct when they are forward bias, but they are arranged in such a way that for one half of the cycle, diode D1 being forward bias conducts and allows the flow of current. In the second half of the cycle, that is the negative half of the cycle, the diode D1 even though blocks the current, but still the current manages to pass through diode D2, which is now forward bias, and conducts. So, the current flows through the entire AC cycle, and thus we get a full wave rectification. Unlike the previous case, over here the DC voltage generated is 2 times Vm by pi, and thus the DC current generated is also 2 times the peak voltage divided by pi times RL. Over here we directly look that the amount of current and the amount of voltage is 2 times as compared to the half wave rectifier, making it a much better kind of rectifier. What we observe is that there are still fluctuations in the circuit. To understand it, let's have a look at what a half wave and a full wave output looks like on the board. For half wave rectifier, we have seen that even though the input is an AC cycle, the output is only for half of the cycle. So, if I show the output on the board, the output looks like this. This is the output of a half wave rectifier, making the efficiency extremely low. On the other hand, when I show the output of a full wave rectifier, for a full wave rectifier, the output is like this. But the problem with the full wave rectifier is that the output is still rippling. There are fluctuations in the output, which means that it is not a perfect DC output. From rectification, I require DC current. There are fluctuations over here, even though both the positive as well as the negative cycle is conducted during full wave rectification. So, we need to reduce this rippling effect and we need to make it a perfect DC. This is done with the help of a filter circuit. Let's understand how a filter circuit leads to lowering of the rippling effect, thereby converting a pulsating circuit current like this into a perfect DC current. This is a simple filter circuit, and this filter circuit plays an important role in converting the ripples which were obtained during full wave rectification. So, after the full wave circuit, this small RC circuit is attached. This RC circuit which is attached over here acts like a filter circuit and it filters out the ripples. So, in this case, what is happening is that when the output comes across D1 or D2, the capacitor during the first half of the positive cycle charges, and when the current starts lowering, the capacitor starts discharging and thereby enhancing the value of the current across the load resistance. This leads to a variation in the output voltage to be minimized. So, what we observe is that with the help of this LC circuit, we are able to filter our rippling effects, or else we get a more strengthened DC signal, unlike the raw signal. Over here, with the help of an LC filtering circuit, we are going to remove the rippling effect which is otherwise seen in a full wave rectifier without a filter circuit. So, by application of a filter circuit, our signal is refined. Let's have a look at our signal. So, over here, a full wave rectifier is connected to an LC filter, and thus the impact of the LC filter is that the output has reduced its ripples and we are getting a DC voltage which is now much more smooth as compared to what we were getting through a full wave rectifier without a filter. Thus, a rectifier is always attached with a filtering circuit so as to minimize the fluctuations. In this way, we are able to convert our AC signals into DC signals, which is the requirement of a number of devices which we use in our households like laptops, mobiles, etc. So, the charger over there is going to carry out this process of conversion of an AC input to a DC input, which is then going to be fed to our laptops, to our mobiles and so on, because these are devices which require DC current. In this particular topic, what we have learnt is the role of diode as a rectifier. How diode carries out the process of rectifier is directly linked to the process of asymmetric conduction of the diode, which means that in forward bias, the diode is going to conduct, while in reverse bias, it is going to block. The diode can act like a half wave rectifier, and we understood the working of a half wave rectifier. Similarly, by a combination of two diodes, we can use it as a full wave rectifier. A full wave rectifier is a much efficient system as compared to the half wave rectifier. We understood the working of a full wave rectifier, and in order to make our signal the output less in terms of ripples, we understood the working of a filter circuit, which is a simple LC circuit, a combination of capacitors and inductors along with the resistance, which helps us in minimizing the rippling effect. These kind of rectifiers are commonly used wherever we require conversion from AC signal to the DC signal. Thank you, learners.